3 pieces of advice, and 2 pieces of the advice are the same as last time. First is to do problems. You don't learn by mathematics by being in a room where mathematics is done. You learn mathematics by working on problems. Now, the good news is we have lots of old exams which are full of problems. I strongly encourage you to look at the old exams. There might be 1 or 2 problems on this upcoming exam which have a vague resemblance, we could say, to old problems. So you should look at those, but not just look at them and read the solutions. Actually try them. Work the problems and then look at the solutions, see how you did. So you can say, okay, do I understand what I'm doing, or do I need to work a little bit more? So there's plenty of problems. Make sure you do them. Take care of your health. That includes getting food to eat, getting enough rest, and maybe going out for a walk if you need to. Keep your regular routine and take care of yourself. And when we say health, we mean mental health. You know, if you need to go scream into your pillow, that's okay. Probably not during the exam, but still, you know, whatever it is so that you go in there in your best shape. You don't want to go in there after you've been sort of mentally drained and start the test that way. That's why you want to end the test. You want to start the test fresh and ready and full of vigor and energy. So take care of that. Now, the last thing is very specific to this test, although it really is true in general. A lot of people, this part of the course, are so focused on the computations that they think that's the thing we care most about. But actually, we care a lot more about the setting up. So what does that mean? We don't care so much that you can do the integral. We care more that you can get the right integral to do. And so you can actually get probably a score of 40 or above out of 60 on this exam without ever actually doing a single integral. Because so many points go towards setting the problem up and getting the right setup. Now, you should do the integrals, but I just want to emphasize, make sure you set the problems up, because that's where the most points are. And as a bonus, if you're doing the wrong integrals, you probably won't get any credit for doing those anyways. And so you want to make sure you're doing the right integrals. And you should know, we're not testing you on hard integrals. So the integrals that you're going to encounter are things that you should be able to do with basic substitution. You won't need any trigonometric substitution. You won't need any partial fractions. If you're doing these kinds of things, that means you probably did something wrong. So check yourself before you wreck yourself. All right. So we're going to start, and we'll begin. On a side note, we will take a short pause, probably halfway through, because we need a pause when we're doing problems. So number 1, let a solid be formed where the base of the solid sits on the xy plane over the region 0 less than or equal to x less than or equal to 1/3 pi, and 0 less than or equal to y less than or equal to secant x, and where the cross sections of the solid, which are perpendicular to the x-axis, are squares, with one side of the square resting on the xy plane. And the problem is, determine the total volume of the solid. Now, what this is saying here is that this is a shape which is not a shape that comes from revolution. So a lot of the things that we looked at were volumes of revolution. So not everything has to be a volume of revolution. So if you look here, this is sort of a picture of what's going on. So the idea is that this is our x, y plane. So we're going from x equals 0 to pi over 3. And then we're going to up to this curve. And this curve back here, this is y equals secant x. So that's what the picture is trying to convey, is that we have this region here. Then we're taking these cross sections which are perpendicular in some way. And if we pick any particular cross section, what we'll see is that the cross section that's being formed is a square. So that's our basic setup. Now, what's the problem? Well, we want to determine the total volume of the solid. So our basic formula for volume, the one we actually started with, is to say the following. Volume is the integral from our start to our stop. And whenever we think of integration, we always think of we're adding things up. So whenever we think of integral, I'm adding a bunch of things up. And what we're adding up are little pieces of volume. And our little piece of volume comes from the following. We're going to take an area times a width. So the A of x is our area, and our dx is our width. So if you take an area times a width, that gives you a volume. Now, which volume is it referring to? It's as if you took a little tiny slice. So you can imagine that I have here this slice here. And if you look at this slice, it looks like a square, which is just a little bit thicker. All right? That's our little piece that we're adding up. Okay, so how do we actually do this problem? Well, now that we have the right formula, that's important, know the right formula, we start figuring out, okay, well, in our case, where do we start and stop? We should integrate with respect to x. Now, why do I say with respect to x? And the answer is because of the way it's been described. Notice how our function is a function of x. Now, it's possible that you can change it and then integrate with respect to y, but almost certainly that's going to make things worse. You should try to integrate with the way that's been given unless there's a compelling reason not to. So we're going to integrate with respect to x. And so we go from 0 to pi over 3. And now, what's our area? Well, the area is the area of the square. And we know that the side of the square on this xy axis corresponds to this length between this curve secant x and this curve y equals 0. So we take one side and then we square it, and then dx. So that's going to be our volume. So now we have to integrate secant squared. And, well, secant squared, it's on our list of integrals to know. Do you remember it? Secant squared, integral? Tangent, good. So tangent x from 0 to pi over 3, which means we need tangent of pi over 3 minus tangent of 0. Well, tangent of 0, that one you should know for sure. That's 0. How about tangent of pi over 3? You probably should try to know it. It wouldn't be the worst thing if you didn't. You could probably leave it here without losing any points if it didn't say simplify as much as possible. But there's always that goal, like, what is it? Do you know what tangent of pi over 3 is? Does anyone? Square root of 3. And that's it. That's the problem. So the hardest thing about this is there's the visualization, but the good news is it gave us a picture. And then the other hard part is to say, well, what is it trying to do? Well, think about cross sections. Add up cross sections times width, the area of cross sections times width. Okay, that's a good warm up. One down. Number 2. Find the volume when the region 0 less than or equal to x less than or equal to 8 and 0 less than or equal to y less than or equal to the square root of x squared plus 10x is spun around the line x equals negative 5. So we have the shape of our region. It's shaded here in a sort of a bluish tone. And we're going around this line, x equals negative 5. You can even see it's saying spin around this line. Now the question is, what method should we use? So this is one of the things, is that we know several different methods. So it's always, you have to think a little bit about what's the right method to use. So one way to start figuring that out is you say, well, what should we integrate with respect to? In our case, what should we integrate with respect to? Which of the two variables? We should integrate with respect to x, because we have things in terms of x. So, okay, we say, all right, if we're going to integrate with respect to x, you think about taking a small x slice. So here's my small x slice. And now we say, what happens to that if we spin that slice around? Well, what happens is you'll see that. So what shape have we just formed? Yeah, it's a cylinder, and we call these shells. So that tells us that if we're going to do our integration with respect to x, which we should, given the way it's been given to us, we should do the shell method. All right, so now we're going to use the shell method. So the shell method, the basic formula, volume is integral from your start to your stop. So we're adding up little pieces of the shell. Then it's 2 pi, the radius to where you spin, the height of what you're spinning, and then a little bit of width. Now, what does that correspond to in our case? So in our case, well, the start and stop are given, 0 to 8. 2 pi turns out, in our problem, is 2 pi. Actually, it turns out it's always 2 pi. That's the nice thing about 2 pi. It always stays the same. Now, what's the radius? Well, the radius is the distance between where you're spinning and the piece that you're spinning. So this part over here, I'm thinking of it as a generic x, and this is negative 5. So what's the distance between x and negative 5? X plus 5. The height is that part. So that's the square root of x squared plus 10x. The width is actually this little tiny length here, and that is the dx. Now I like to write it as width because it might be that you might be integrating with respect to y, and then the width becomes dy. But every single term in an integral represents something. And once you understand what things represent, it's much easier to just say, okay, here's the basic format, and now I'll just put in the pieces as I need. You don't want to try to memorize 100 different formulas. You want to just memorize sort of a few, a dozen different basic forms, and then you're good to go. Now, if you just saw the square root of x squared plus 10x, you might start having flashbacks to the last exams, like, oh my gosh, we had something like that in the last exam. It did not go very well for me. But remember, we're not doing stuff from the last exam. So you have to think, okay, there's got to be a better way. Now, is there a better way? And what can we do?
Multiply x plus 5 times 2.
Well, we could, but also, that's building up to what? Well, notice the x squared plus 10x. If you said u equals x squared plus 10x, what would du become? 2x plus 10 dx. And if you take the 2 and the x plus 5 and the dx, lo and behold, that's your 2x plus 10 dx. So that's pretty good. So this becomes the integral from, well, let's work on that in a second, pi. The square root of x squared plus 10x is the square root of u. But because we're doing calculus, we write that as u to the 1/2. Then the 2 times x plus 5 dx becomes our du. And then we have to update our bounds. Now 0, that's our old bound. That's an x bound. We're switching to new bounds. We're switching to u bounds. So x equals 0. 0 was our old bound. Our new bound is 0. Because you plug 0 in, 0 squared plus 10 times 0. Now 8 is more interesting. Plug in 8. 8 squared plus 10 times 8? 144. All right. So, what do we get? Well, we integrate. Integral of u to the 1/2. Well, you'd add 1, u to the 3/2, multiply by 2/3 in front, and don't forget the fact that there's a pi. You should be suspicious if you have a volume of revolution and there's not a pi in your final answer. It's very unusual. 0 to 144, and okay, so that's pi times 2/3 times 144 to the 3/2, and then we subtract, plug in 0, we get 0. Now, could you leave your answer like this? Yeah, you could. Yeah, you could. Now, if you wanted to, you could also say that this is 1,152 pi. You'd also get credit if you did that. Now, either one gets credit. In case you're wondering, did he memorize that? Maybe. But it's actually not so hard to figure it out. Because think about 144 to the 3/2. 144 is not just any casual number. What is it? It's like 12 squared. So I can really think of this as 144 times the square root of 144, because I can think of it as 144 to the 1 times 144 to the 1/2. Now, square root of 144 becomes 12. But then I also have a 2/3. 2/3 times 12 would be what?
8.
So I can write it as 8 times 144, which I can think of that as 800, because that's 8 times 100, plus 320, which is 8 times 40, plus 32, which is 8 times 4. And if you add all of those up, you get 1152. But either one would receive the points. And if you're in a test situation, probably you should stick with this one. Because if you simplify and you make a mistake, you could lose points. No, let me rephrase that. You'll lose points. So The moral is, get the answer to a place where you'll get the credit, and then stop. All right? Good. All right. Well, let's try another one. So find the volume when the region 0 less than or equal to x less than or equal to half pi, and sine x less than or equal to y less than or equal to 1 plus cosine x is spun around the x-axis. And it draws the basic shape for us. It didn't label the curves, but that's not too hard to figure out. Sine x is the one down here. 1 plus cosine x is the one up here. Now, when we're integrating, what are we going to integrate with respect to? We're going to integrate with respect to x because we have functions of x. So that says we're going to take our little slices. These are little x slices. When you spin these little x slices around, what shape are we going to end up forming? Washer. So that tells us this is a washer problem. So we can figure it out based on what happens to a little piece. Because integration is all about adding up the little pieces. So we know this is a washer problem. So for washer, we say that the volume is equal to adding up little pieces from A to B. So integration is always about addition. You're adding lots of pieces up. And we're going to take pi times what we call the outer radius squared. And then we're going to subtract pi times the inner radius squared. So we can actually factor the pi out. And that's our generic formula, and then we times it by our little width. It actually goes back to the first formula we talked about, where we say, oh, look at the volume of a little slice. And what's happening is that this pi times outer radius squared minus pi inner radius squared, that's the area of a slice. So there's our generic formula. Now we just apply it to our specific case. So, what do we have? Well, where do we go from? Where are our bounds? 0 to pi over 2. And then we have pi. Well, what's our outer radius? And again, the outer radius, we're going from x equals 0. So the outer radius is the furthest one away. So that is 1 plus cosine of x squared. Minus, what's our inner radius? The one closer. Sine of x. Now that's because we're spinning around the x-axis. You could imagine that we were spinning somewhere else. You could imagine we were spinning, say, way up here at x equals 3. Then the inner one will be the one to 1 plus cosine x, and the outer one would be to sine x. Just pay attention. Pay attention. So, well, to integrate, probably we should first simplify. We square that out. We get 1 plus 2 cosine x plus cosine squared x. Then subtract sine squared x dx. Now, is there any way we can simplify this? Cosine squared x minus sine squared dx. Yeah, have we ever seen anything like that before? What is it? Double angle formula. One of those nice trig identities. And you might be wondering, do I need to know those trig identities? Yes. Because we haven't gotten to it yet, but we're going to end up at polar by the time we hit the end. And polar has tons of trig identities built into it. So you got to know your trig identities for polar. So 1 plus 2 cosine of x plus cosine 2x dx. So we're ready to integrate. Pi, then the integral of 1. Well, that's not bad. That's x. Integral of 2 cosine x. 2 sine of x. The integral of cosine 2x. 1/2 sine of 2x. All right, evaluate from 0 to pi over 2. When you plug in pi over 2, well, you're going to get pi over 2 from the x term. Sine of pi over 2, do you know that? Sine of pi over 2 is 1, so 2 times that is 2. Sine of pi, 0. Okay, so we don't need to write that term. Now we plug in 0. 0, turns out, is 0. Sine of 0, 0. Sine of 0 is still 0. So there's our answer. pi times pi halves plus 2. All right. Good. Whew. Good times. Okay. Given that f of x is greater than or equal to 0, and that when the region 0 less than or equal to x less than or equal to 4, and 0 less than or equal to y less than or equal to f of x is spun around the x-axis, the volume is 22 pi. And when the same region is spun around the y-axis, the volume is 14 pi. The question is, determine the volume when the region 0 less than or equal to x less than or equal to 4, and 0 less than or equal to y less than or equal to 3x plus 2f of x is spun around the x-axis. No picture on this one. Okay, that's all right. That means we can draw our own picture. All right, so we draw a picture. And the good news is we don't have to be accurate. All right, here's f of x. Here's 0. Here's 4. Here's our region. Now, is that right? Probably not, but that's okay. I just need to get an intuition, and that's enough to get an intuition going. So we work through what has to be true. So we're going to just dissect these statements. Here's the first one. When we go around the x-axis, the volume is 22 pi. So if we spin this region around the x-axis, what technique would we have to use? Disk. It's the disk method. So we can say that 22 pi is equal to the integral 0 to 4 of pi times the radius squared. So the outer radius is f of x and the inner radius is 0. So it simply becomes pi times f of x squared dx. All right. So that's the first statement. And then there's another statement. Namely, suppose we went around the y-axis, the volume is 14 pi. So around the y-axis, we get 14 pi. Well, what method do we have to use if we go around the y-axis? Shell method. So we get that 14 pi is equal to integral 0 to 4, 2 pi. Well, what's our radius? It's x, because we're just going out to a generic x. And our height is f of x. And our dx is dx. That represents our width. So those are the two pieces that we're given. We're given information, and we can translate that into formulas. So oftentimes, a lot of what math is saying, here's one piece of information given to you in a certain form using words. Translate that into an equation. Once you have an equation, you're like, oh, I have tools that help me manipulate equations. So it's learning to read the statement and translate that into a nice mathematical format. All right. So now we have this kind of curious function, 3x plus 2f of x. Now, I don't know exactly what it looks like, but it's probably doing something like that. Here's 3x plus 2f of x. And it should be going up higher. And we're going to spin it around the x-axis. So, what are we after? Well, if we're going to spin that around the x-axis, what's our technique? Yeah, still going to be, well, it's going to be a disk, because there's no hole in the middle. But yeah, it's the washer method. So, we're after the integral 0 to 4 pi times 3x plus 2 f of x quantity squared dx. That's our answer. So in some sense, we could say that this long statement translates into, here are two things that we know, and here's something we want to find. And if you give it the problem to us in this other format, we're like, oh, okay, we can work with it. So it's translation. So let's work with this. What's something we can do to this integral? We can expand. So we square that out, get 3x times 3x, 9x squared, plus, then we have the cross terms. So that would be plus 12x f of x, and then plus 4 times f of x squared dx. Now, we'll break this up into pieces. So our first piece, Well, that'll be 9 pi, integral 0 to 4, x squared dx. All right. Now the next piece, we look at this and say, hey, this looks amazingly like the f of x part. And we have a pi, so we're like, okay, let's take this 12 and think of it as 2 times 6. And if we do that, I can write this as 6, and then we'll have 2 pi x f of x. So just sort of anticipating that I want to use the information that I know. On the last part, what will I do? Well, there's still a pi, and then it becomes pi f of x squared, and then there's a 4. Pull that out. 4, integral 0 to 4, pi f of x squared. Now, a few of these we can do really easily. This last one, what does this become? 22 pi, and then there's a 4, so this will become 4 times 22 pi. How about this middle piece? That's a 14 pi, then there's another 6, so that becomes 6 times 14 pi. And then there's this part, which they didn't give us any information for. But that's okay, because we know how to integrate that part. Integral of x squared? Yeah, 1/3 x cubed from 0 to 4. And if you times that by 9 pi, well, what you'll end up with here is 3 pi times 4 cubed, which is 64. All right, so finally, we put things together. 3 times 64, that's 192 pi. 6 times 14, that's 84 times pi. And 4 times 22, that's 88 times pi, which means there's definitely a lot of pi here. Now, from here it's not too terrible. If we think of the 192 plus the 88, if you add 8 to 192, you get to an even 200. So 192 plus 88 would give us to 280, plus an additional 84 on 280 would give us 364. 364 pi. It's almost like we had a pi a day, but then we took a day off, maybe Thanksgiving. Who knows? So that's it, 364 pi, and we're done. Good. Well, that's it for our volumes, at least for now. There's lots of other things we can do. So, number 5. Find the length of the curve y equals the natural log of x plus the square root of x squared minus 1. For 1 less than or equal to x, less than or equal to square root of 5. Now, your first inclination on seeing this is, I thought you said we weren't going to have to do any hard integrals. Well, hold on. Be patient. Just because the problem looks hard, it might become simple if you're patient. So let's see what we have. So this is the length of the curve. Now there's a bunch of variations of length of the curve, so you should know all of them. So let's quickly go over them. So the 3 that you should know, there's y equals f of x, which is our variation. So for y equals f of x, what you would do is you integrate from a to b the square root of 1 plus f prime of x quantity squared dx. All right, so that's the arc length if you're given y as a function of x. And essentially what the idea is you say, okay, the idea is you break things up into tiny little pieces, and then you say, how long is one little tiny piece? And the answer is, if you go very small, it's square root of 1 plus f prime of x squared. That's what's happening. Now, another variation is you might have something in parametric form, x of t, y of t. And if you have parametric form, for that, you integrate a to b. And here, a and b are your time. Where do you start time? Where do you stop time? And then it's a square root of x prime of t squared plus y prime of t squared dt. The last one, which you may or may not quite have done, but you'll know it by the test, is in polar. So there's the y equals f of x, parametric, and the polar. The polar one is actually kind of nice. Instead of a and b, we like to use alpha, beta for polar, because we like to think of polar as being angles, and so we give things angle names. And that one is the square root of f of theta squared plus f prime of theta squared d theta. So those are the three variations. You should know them all. But they all more or less have the same spirit and philosophy. In fact, if you don't want to memorize all of them, you can always say, look, every time you have a polar curve, you can always turn it into a parametric curve very easily. And so you can sort of memorize one thing less. The two most important are the first two, y equals f of x and your parametric. But they all have something in common. What do they all have in common? Yeah, they all have a square root. So whenever you see a problem that involves arc length, and also later on when we talk about surface area, we're always going to have to deal with square roots. So the question is, how do you deal with a square root? What's our strategy? Well, if we were being fancy, we'd do trig substitution, but now we don't have to be fancy. That's not this test. On the final, we can be fancy, because then we bring it all together. So yeah, we don't have to worry. Don't think like, oh my gosh, if you're starting to pull out trig substitution, you've done it wrong. There should be no trig substitution. So what are some other things we can do to look with square roots? Well, right, look for substitutions, u sub, but also look for perfect squares. Because oftentimes, miraculously, the things inside the square roots have become a perfect square. Okay, but let's see, is there anything else? That's almost it. It's not a very long list. So, if you don't see one of these two things, u sub or a perfect square, what should you do? Yeah, go back and check your work. Because probably something happened. We've made sure that these are problems we can do. So if you're like, I don't know how to do this, either you're missing something or you've made a mistake. And either way, start again. You don't have to erase everything. Just start going through and checking your work. So, okay, so let's go and start the process. Here we go. So y equals natural log x plus square root of x squared minus 1. We're in this format here. And we have our bounds. 1 to square root of 5. 1 square root of 5. And then we have the square root of 1 plus. Now we have to take the derivative. That'll be fun. Derivative of a natural log, well, that's 1 over what's inside. X plus square root of x squared minus 1. And then we're going to times that by the derivative of the inside. And of course, this is all going to be squared in a second. The derivative of x, 1, plus, and now the derivative of the square root of x squared minus 1. Well, the square root of x squared minus 1, you can think of that as x squared minus 1 to the 1/2. So that would be 1/2 x squared minus 1 to the negative 1/2 times that by 2x. All right, there's our derivative. We're going to square that, dx. Okay. Now, if you see this, don't have your gut reaction be, I can drop a problem. That should never be your reaction on any of these things. Your reaction should be just, I have trust in my ability to compute things. I'm going to go on faith that they gave me something that's going to work out. Okay? So that's our philosophy. We're not going to drop anything. Try all 7. Now the 2's cancel. That's a good sign. And if you look at this term right here, another way to write this is 1 plus x over the square root of x squared minus 1. That's just the second part. What's another way to write that? Well, if you want to add them, you get a common denominator. So you can write it as square root of x squared minus 1 plus x over the square root of x squared minus 1. Yes? Yeah. And over here, remember, we have 1 over x plus square root of x squared minus 1. And this is all being squared. What do you notice? They cancel. And now, remember that you have to square it. So, being careful, which is a very good strategy, we end up with 1 plus 1 over x squared minus 1 dx. But we're still not done. We can continue to simplify. What else can we do? Add them together. So this can become x squared minus 1 over x squared minus 1 plus 1 over x squared minus 1, which in our case becomes simply x squared over x squared minus 1. All right? And now what can we do? Oh, that should be a 5 upstairs. I don't know why I put an x. Now what can we do?
Factor out an x.
Okay, so we can pull out an x. So, is it true that 1 over square root of 5 times the square root of x squared over x squared minus 1 is the same as x over square root of x squared minus 1? Is this true? Why? Let's be careful here. Is it true that the square root of x squared is x? It's absolute value of x, so be careful if you're taking a square root of a square. Now in our case, are we okay? Yeah, because x is positive. So we're in between, we're positive, so we are fine. If we weren't, we would be like, be careful, be careful. Okay. So we're good, we're good. This is, yeah, good. All right. Now, that feels like something we can do. What can we do? Yeah, we can use u substitution. So we'll set u equal x squared minus 1. And du will be 2x dx. Or if you like, you could say that using our fancy paper technology, 1/2 du is x dx. So updating, we have that this is the integral. So the x dx becomes a 1/2, I'll pull that out, du. The square root of x squared minus 1 downstairs becomes what? U to the what power? Negative 1/2. Negative because it was in the denominator 1/2 because it was a square root. What are the bounds? It's going to be 0 to 4. Yes? Because 1 squared minus 1 is 0. The square root of 5 squared minus 1 is 4. All right. Well, 1/2 times the integral of u to the minus 1/2. Integrate u to the minus 1/2. You get u to the positive 1/2. Multiply in front by 2 over 1. And then we're going to evaluate from 0 to 4. The 2's cancel. The 1's cancel. Of course, that doesn't really do anything. Square root of 4. 2. Subtract square root of 0. Well, that's 0. So the answer is 2. So that's it. Now, you may have noticed something, and you may think that, didn't we cheat a little bit? What's true about this integral? Well, it's actually improper. Do you see why? Well, because your derivative at 1, it's actually coming in straight down. But here's the cool thing. A lot of time improper integrals take care of themselves. And if they do, you don't have to worry. Don't worry if you see an improper integral. Just be like, yeah, it takes care of itself. Life is good. Life is good. For this test, yes. For the final, oh, the final is good. Because on the final, see, on this test, we're trying to focus on just the parts of applications. Whereas the first test was just the parts of integration, the fun, fancy integration. On the final, we get to make a beautiful mixture, a wonderful cake. I've been watching the Great British Bake Off recently, so I've just been thinking of cakes and pies. All right. Number 6. Find the surface area when the parametric curve x of t, which is equal to t squared plus 8t, and y of t, which equals 2/5 t to the 5 halves plus 8/3 t to the 3 halves, is rotated around the line x equals negative 16. Okay. Well, let's just, we don't panic. We're like, okay, there's a process here. I don't know what the curve looks like. So I'll just make something up. Oh, there's definitely a problem with this problem. Okay, we should come up with some bounds. I didn't give bounds here. Well, let's make some bounds up. What bounds should we pick? 0 and 1? Okay, all right. Sorry about that. For 0 less than or equal to t, less than or equal, let's see, is 0 and 1 going to be a good number? Well, we'll regret our choice of 1 later on. All right. We almost never regret a choice of 0. 0 is a wonderful number. When you can work with 0, you should work with 0. Okay. So there we go. We're going to add that condition. Okay. So we have this parametric curve. We have this line, x equals negative 16. So that's what x equals negative 16. Our parametric curve is doing something over here. And we're going to spin. And because we talk about the rotation, that means we're spinning. So we're spinning around this line. All right. So our goal is surface area. So we should know the surface area formulas. Now the surface area formulas, we can actually condense them because they all have the same form. So for surface area, we are adding up from our start to our stop. It's 2 pi times 2 pieces. The radius and the length. That's it. That's what you remember. 2 pi, radius, and length. Now you might say, where is the length coming from? The answer is just depends on your context. So the length is these pieces that we did when we talked about arc length. So it's square root of 1 plus f prime of x squared dx. That's if we're of the form y equals f of x. That's square root of x prime squared plus y prime squared. Okay, that's if we are in parametric, and similarly and so forth. So these parts are the length. So when we talk about length, we mean these things. All right. So in our case, we're parametric, so we're going to be using that expression there. Oh, actually, I think t minus 1 should be okay. Oh, can we change it to 4? Yeah, let's change it to 4. Yeah, 4 is a better choice. I like that. Yeah, 4 is a better choice. Okay, all right. I'll probably regret the choice of 4 later on, but for some reason 4 sounds really good to me right now. Okay, so where are we going? Well, we have our piece. Now, when we think of surface area, we really think of saying, I'm going to just take a little piece of the curve. So it's not like we're doing a piece of area. No, it's a piece of the curve. So the radius is from the curve to where you're spinning. So this is the radius. So in this case, we're spinning around the line x equals negative 16. So it's going to be that. If we spun around a y equals something, it would be done the other direction. So the question is, for us, what is that distance? It's x plus 16, because we're thinking of this as the point x, y. And we can think of x, y in any setting. We can say, okay, so it's x could be a parametric setting, so x of t, y of t, or we could have x equals f of x, all sorts, or y equals f of x, all sorts of things. So for us, it's going to be x plus 16. Now, for us, x is parametric, so in particular, we're going to have our x of t plus 16. So we're going to have t squared plus 8t plus 16. Okay? That's our radius. 2 pi, still stays as 2 pi. We're going to go from 0 up to 4, because we changed it from 0 to 4. All right. Now, let's see. Now I'm debating. Maybe 0 and 4 weren't the best. Maybe 0 and 5. Yeah, we'll stick with 4. Okay. I'm sorry. I should have remembered to look this up. What do we use for length? What's our formula going to be? Yeah, this is a parametric, so the length is going to be square root x prime t squared plus y prime of t squared dt. That's our length. So we have a little bit of work ahead of ourselves. What is x prime? So 2t plus 8, and we're going to square that. Plus, what's y prime? T to the 3 halves plus 4t to the what? 1 half? Yeah, because if you bring down a 3 halves, 8 thirds times 3 halves is 4. Okay, and then that's going to be squared. And then we're going to take the square root of that. Okay. Square root. Square this out. You'll get 4t squared. Then you're going to get the cross terms. 2 times 8, then double that. So that's going to be 32t. And then plus 64. And then over here, we square this. We're going to get t cubed plus the cross terms. So that would be 8. So the t cubed, by the way, is t to the 3 halves times t to the 3 halves. What's going to be the middle term? 8 what? It'll be t squared. T to the 3 halves times t to the 1 half. That's t to the 4 halves. Okay, are we done? No, because there's a suspicious space here. The last term, 16t. All right. So, taking that, we can write this as t cubed plus 12t squared plus 48t plus 64. Okay, so that's our length, dt. So this part here is what goes there. So, writing it, 0 to 4, 2 pi, t squared plus 8t plus 16 times the square root of t cubed plus 12t squared plus 48t plus 64 dt. All right, what can we do here? Oh, we can try a u sub. It might work. What can we try for our u substitution? Yeah. Try the whole inside, right? That's like, I really hope it works. I mean, it might. Stranger things have happened. Whoops, getting ahead of myself. T cubed plus 12t squared plus 48. It would be amazing if this worked. Be amazing. Du, what is it? 3t squared, 24t, 48. Ah, man. Oh, wait. Yeah. 1/3 du would be t squared plus 8t plus 16. Nice. Okay. Cool. So, this becomes integral 2 pi. And let's see, this t squared plus 8t plus 16 dt is 1/3 du. And then this square root becomes a u to the 1 half. And then we have to do our bounds. Well, when you plug in 0, that's not so hard. You'll get 64. Now, if you plug in 4, well, I am starting to regret 64. Let's change it back to 1. We'll go back to 1. Now, if you plug in 1, okay, I can do that one. Maybe. No, it's 125. I mean, we don't need to pretend. It's there. Okay. Yes? Because you can see there's the 12 plus 48 makes 60. Adds that to 64 is 124. Then there's one more makes 125. Okay, so what do we get? Well, 2/3 pi, u to the 1 half, integral that. U to the 3 halves times, in front, another 2/3. So we end up with 4/9 times pi times, and this is evaluated from 64 to 125. And, 125 to the 3 halves minus 64 to the 3 halves. Okay. That looks about as simple as we can hope. Now, on a side note, you could have done this in a slightly different way. What's another, you don't need to know this fact, but this is just a fun like, ooh, wow, what? Cool. Okay. Oh, we should have changed our bounds because we changed them to 0 to 1. Okay. T squared plus 8t plus 16 is t plus 4 squared. T cubed plus 12t squared plus 48t plus 64. That one's a little bit harder. It turns out it's t plus 4 cubed. Square root. So it's actually t plus 4 to a power times t plus 4 to another power. So if you put them together, what you'd end up with is the integral from 0 to 1 of 2 pi of t plus 4 to the power 2 plus 3 halves, which is 7 halves. And then if you integrate that, lo and behold, integral of 7 halves, you'd add 1, you get 9 halves. Then you multiply by 2 ninths, which would give you 4 ninths pi, t plus 4 to the 9 halves from 0 to 1. And then you'll get the same answers. All right, cool. Yes?
Well, why could we choose the A and B?
Well, because I forgot to write down what the A and B were. On a problem, they won't forget.
Oh, I see.
Don't worry. The problems have been thoroughly vetted. They pulled out a microscope and they said, this picture could be a little bit better. So we made good pictures. Good pictures. That's why we could choose A and B. All right. Let's try another one. Okay. You find yourself going up a flight of stairs, which is 10 feet in elevation change. So here you see a flight of stairs. So you're going to go up. It turns out there's 10 stairs here. I think there's 10. Anyways, 10 feet. Now you're carrying a container which weighs 10 pounds and is shaped as an upside down cone with the height of the cone 3 times the radius. Now before going up the stairs, the container is filled with the fluid to a depth of 30 inches. And the fluid has a density of a ½ pound per cubic inch. Now as you move up the stairs, the fluid leaks out. And the depth of the fluid drops at a constant rate. And when you reach the top, the depth is just 10 inches. So you lost a lot. It's very dangerous to walk up those stairs right now. Determine the work done in carrying the container and its contents up the stairs. And include units in your answer. All right, so this is really a cross-section because it's a cone. It's not a triangle. So it's really a 3-dimensional picture. But for drawing convenience, it's easier to draw these as triangles. So you can see that at the bottom, there's a lot. At the top, not so much. Okay, so how do we answer this? Well, there's a few things that you need to know. One thing you need to know is the volume of a cone. Normally, if it was important on a test, we would give you the volume of a cone because we don't want you to be stumped. Do you know the volume of a cone, by the way? Anyone? So the volume of a cone is, there's a 1/3. 1/3 pi r squared h. So the pi r squared, this is if you have a cone that looks like this, where r is your radius at the bottom and h is your height. Okay, so that's something that is useful to answer this question, and we would give you on an exam. So if we're trying to find our work, and the reason that I know we're looking for work is it says determine the work. So that's sort of the giveaway that this is a work problem when it says do the work. All right. So if we're trying to find work, your basic expression for work is you add up your force times your distance. So this is your force, and this is your distance. Okay, and then that finds your total work. So the force times distance is just little tiny pieces. Now in our case, it might be easier instead of integrating with respect to x, because we're thinking about a vertical motion, we should probably think about this in terms of y, just because our minds are really geared that way. So I'm going to think about this, rewrite it in terms of y. Now, whenever you have a problem, one of the first things you want to do is start to assign coordinates. So at the bottom, what should we correspond our bottom to be? Yeah, that's a very logical thing to do. And the top, what would that be? 10. So for us, that tells us that we're going to go from 0 to 10. Our distance is just moving up a little bit. That's our dy. So we're going to have a big piece, then we're going to do a dy. Now the force is, you can think of it as weight, because the force would be measured in pounds. So we have two things that weigh something. One thing that we have that's weight is the container itself. How much does that weigh? It weighs 10 pounds. Now the container doesn't, it's not like we're dropping pieces of the container off. We're not like breaking it off as we go up the stairs and throwing it on the floor. So the container is always going to be 10 pounds all the way up. So that weight is steady at 10. But there's also the weight of the fluid. So for the fluid, we're going to have to add on that weight. So now we have to think about the weight of the fluid. So we know a couple of things. We know that we're dropping. Our initial depth is 30. Our final depth is 10. So what's our depth at a given y? So again, at y equals 0, we are 30. At y equals 10, we are 10. In the middle, what would we be? So if we're going at a, and you should point out that we're dropping at a constant rate. So how much did we lose? What's our depth difference? 20. So we lost depth of 20 when we went up by 10. So that says we're really losing 2 inches of depth per foot up. So the formula, we could say, is the initial depth subtract 2y. Okay? Now, unfortunately, that's not quite our weight. So now we have to translate that depth into a weight. So to do that, we say, well, I know the density is 1/2 pounds per inches cubed. So if I take 1/2 times the volume at a certain height, then that will give me my answer. Okay? So we're getting close. We're getting close. So now we come back and we say, okay, what do we know about this container? It's an upside down cone. The height is 3 times the radius. So the height is 3r. And the depth is just a fancy way of saying the height of the fluid. So if we come here, if we say height equals 3r, we could say that the radius is 1/3 the height. So that the volume coming into our cone, the volume of the cone would be 1/3 times pi times 1/3 the height squared times the height, which is going to be pi over 27 h cubed. So our volume is pi over 27 times 30 minus 2y cubed. All right. So again, the 10, that's our container. And then we have the density times the volume of the fluid. And we use the fact that we know the shape of the cone to rewrite it just in terms of the depth of the fluid, which is the height. And we figure out what the depth is at any given time. So that's definitely, we've done really the hard work. Like if this were a problem out of 10 points, if you got to here, you got like 7 out of 10. You know, so this is definitely the kind of stuff we value, is getting to this stage. Now the rest of it is just you integrate. So if I integrate 10, what does that give? 10y, if we're integrating with respect to y, plus pi over 54. Now, one thing you could do is, of course, you could, whoops, I said 52, but I wrote 54. Pi over 54, 2 times 27. You could expand 30 minus 2y out, and then do various other terrible manipulations, but we don't have to do that. This is one we could probably do in our one line. It would be 30 minus 2y to what power? To the 4th power. But then I'd have to divide by 2 things. What would I have to divide by? 4 because of the power, and negative 2 because of the negative 2 on the inside. You can also do this by substitution. And now we're almost there. You evaluate from 0 to 10. So, that's we're running out of room. We're going to get 100. And then we're going to have 54 times 4 times 2 is a big number, 432. Not that we need to know that. But minus pi over 432. And we plug in 10, we're going to get 30 minus 20 to the 4th, which is a big number. It's one with the 4 zeros after it. Subtract, so that's when we plug in 10. When we plug in 0, well, we plug in 0, 10y, you get 0. And then we're going to get a minus makes a plus, pi over 432. And then we're going to have 30 minus 0 to the 4th. Well, that's an even bigger number, which you could probably leave it as 30 to the 4th. If you wanted to, you can multiply that out. 30 to the 4th would be 810,000. So that's our work. And we could just leave it like that and get our answer, and we're going to just leave it like that. But there's one other part, if we want full credit. It says include units. So if you leave off your units, you're going to lose a point. What's the units of work? Foot-pounds. How do we see it? Go back to what we're doing. Force is a pound. Distance is foot. Foot-pounds. Okay? All right. All right, we still have a few more problems to get through. Now, I don't want you to be nervous and think like, oh my gosh, this is like how hard a problem is going to be with the numbers. The numbers on the exams have been carefully worked to be nice. The reason I wanted to do this one is just to say, like, this is a very different problem in that your weight isn't dropping at a constant rate. So you really do have to use calculus here. You can't just sort of like, oh, it's kind of like dropping at a constant rate. I can sort of cheat a little bit. No, we don't want you to do that. We want you to do it the right way, the calculus way. Okay. Time for our next problem. A small pool has been formed by rotating the part of the hyperbola x squared minus y squared equals 9 for 0 less than or equal to y less than or equal to 2. So that is to say, if you came here and you went from y equals 0 to y equals 2, then you have this piece here. This is your hyperbola x squared minus y squared equals 9, and you spin it. And you spin it around the y-axis. So here we go. So all right, that's our picture. Also, all the distances are measured in feet. And we're going to call this the hyperbola, because it's formed a little pool. So currently the hyperbola is filled with water, which has a density of 60 pounds per cubic foot. And it will be emptied by pumping it up to a storage container. So there's our storage container, which has its intake located 6 feet above the top of the hyperbola. So the question is, what's the total amount of work it will take to transfer the water into the storage container? Now, it didn't ask us to do it. We should probably also throw pounds in just at the end. Now, this is another work problem. So pretty much when you see a work problem, the units are freebies. They're almost always foot-pounds because that's how we talk about work here. Us Americans in our old system of measurements. So how does this work? So this is a pumping problem, and all pumping problems have the same setup. So the idea is we're going to do the following. We're going to add up how much work it takes us to move a little piece. And the way we find the work to take a little piece is the following. We think of like having a very small section, and we're going to slice it. So here's a small slice of our hyperbola. We're going to say, okay, how much work does it take to move this piece up? Well, so there's a couple of things we need to know. There's a distance, which is how far we have to move it. And then there's the weight, the pounds. And the weight gets broken down even further. So the weight, we need to have a density, how heavy it is per amount of volume. Then our volume is the area of a cross section. And then finally, we need a little bit of a thickness. And our thickness here, that's talking about this up-down part, that's going to almost always be our dy, because we're going to think about things in terms of y. So a couple of these are pretty quick to figure out. The density is almost always constant, and for us, it's 60. The distance, you say, okay, where do I need to move it? Well, before you do anything with distance and area of cross sections, you'd really have to say, where are my coordinates? But on this problem, we don't have a choice, because the way our pool was described to us already had coordinates built into it. So we already know what our coordinate system is. So our distance says, I want to go from a height y up to this height up here. Now, what is this height? It's 8. Because remember, it's 6 feet above the top of the hyperbola, but the hyperbola has a height of 2. So our distance is 8 minus y. That's how far we have to move our thing. Finally, we look at the area of a cross section. Well, this we should feel really comfortable with, because we were told it's found by rotating. So this is a shape that comes from a rotation. So the cross section, what does a cross section look like? It's a circle. The area of a circle will be pi times the radius squared. Now the radius is the distance out to your x. So the x coordinate. So pi x squared. Now, of course, this is not satisfying because we need to write it in terms of y. But what can we do with x squared? We can replace it. Because you notice what it says. X squared minus y squared equals 9. So I can solve for x squared and say that x squared is 9 plus y squared. So the area of my cross section is pi times 9 plus y squared. And now we're in pretty good shape. We can pull out the 60 and the pi. So we get 60 pi. Oh, and I should have said where are our bounds? Well, 0 to 2. The depth of our hyperbola. So 60 pi, 0 to 2. Now to integrate 8 minus y times 9 plus y squared, you would just expand. So for instance, you'd have 72, and then you'd have minus 9y, and then you'd have plus 8y squared, and you'd end up with a minus y cubed. So I multiplied 8 minus y times 9 plus y squared out. Now from here, we say, all right, we can integrate term by term. Integral of 72, 72y. Integral of y is 9 halves y squared. 8y squared, 8 thirds y cubed. Then y cubed is y to the 4th over 4. Now these numbers don't look great, but we could also, we could multiply the 60 through. We wanted to. We can. 60 times 72 is, right, 4,320. Good. Now, you're probably wondering, how are you doing that? Well, I'm bluffing. You don't know if I'm right. But really, 60 has the advantage in that there's a 0 on the end. So I can think of it as 6 times 72. 6 times 70 is 420. 6 times 2 is 12. Put those together, you get 432 plus the 0. So 4,320y. 60 times 9 halves. How about that one? Well, 270, because you can divide it into 2. 60 times 8 thirds. 160, because I can divide 60 by 3. That's 20, and 20 times 8 is 160. 60 divided by 4? 15. And we're going from 0 to 2. If you plug in 0, the good news is everything is 0, so you just have to plug in 2. So you end up with pi times 4,320 times 2, that's 8,740. Nope, that's not true. That's 8,640. Thank you. 270 times 4, 1080. Like the resolution on nice TV sets. 160 times 8.
512. 5,120.
So what is it?
5,120.
160 times 8? I thought it was be 1,280. What is it? Yeah? Okay. Cool. 15 times 16. 240. Now, again, don't get too nervous. These have not been vetted very well. 1080 minus 1080 plus 1280. What does that turn out to be? 200. If I take 200, subtract 240, negative 40. And now if I take 8640, subtract 40, 8600 pi. And we throw in units, even though they didn't ask, foot-pounds. By the way, if it asks for units, you don't have to always have your units while you're doing the problem. Just put it in on the end. If you do your problem right, the units will always be correct. So okay. Actually, that turned out to not be such a bad number. Okay. Number 9. You are tasked with constructing a custom rod of length 2 so that the total mass of the rod is 6 and the center of mass, or the balancing point, is at x bar equals 7/9. So we have this rod, and so we're going to think of it as going from 0 to 2 because it tells us the rod is measured from 0 to 2, and the center, of course, would be at 1. 7/9 is a little bit over here. So we don't want the rod to be like perfectly uniform. Perfectly uniform, the centering point would be at 1. So it balances at 7/9. And we know that the total mass has to be 6. So the way we do this is we have to somehow manipulate the rod. And we can do it because the process you have allows you to set the density to be AX plus B. So we want to determine the values of A and B that will produce this rod. So we say, okay, so this involves a mass and a center of mass. So let's talk about that. Now, how do you find mass? Well, mass is all about adding up your little pieces of mass. So we're going to go from, say, some point C to some other point D. And what we do is we multiply a density times a length. So this is a one-dimensional version because we think of a rod as being a one-dimensional thing. So this is our density, and this here is our length. And there's lots of variations of mass problems because you can have mass of a one-dimensional rod, a two-dimensional region, or even a one-dimensional curve. But there always are the same philosophy. So if you're dealing with a straight rod or with a parametric curve, density times length. If you're dealing with a two-dimensional region, density times area. Now for us, that says, okay, that's going to be 0 to 2. Those are our endpoints. Our density is AX plus B, and our dx is our dx. So that's not hard to figure out. And our mass, we were told, is 6. So, pushing this a little bit further, what do we get? So that's integral, that's 1/2 ax squared plus bx, evaluate from 0 to 2. And when we evaluate, what do we end up with? Well, plug in 2. 2 squared, 4 times 1/2. It's 2a plus 2b. And plug in 0, you get 0. So 2a plus 2b has to be 6, which tells us that a plus b had best equal 3. So that's assuming we get the right mass. A plus b had better be 3. Now that's not enough alone for us to determine what we need. But we also have a second condition. We need the center of mass. Now the way you find the center of mass is you take a moment and you recall that there's a formula. So the moment formula. It says, so the moment, m0, this is found, so this is the moment. The 0 here, that's not an O, that's a 0. That means every moment is taking a look at a combination of a mass with location. You can think of it as mass and distance if you like, but mass plus location. So when you talk about location, location with respect to something. So for us, we're talking about with respect to 0. So for one-dimensional thing, it's going to be the integral from c to d. Your location will be x, delta x dx. So again, your delta x dx is the mass of the piece. This x is the location of your piece. Okay. So what do we know? Well, we know a couple of things. We know we want our center of mass to be at 7/9, because that's what it says. We also know we want our mass to be 6, because that's what we're after. So m is 6. So we could rewrite this if we multiply both sides by 6. That becomes 14 over 3, because I can cancel off a 3 between the 6 and the 9, has to equal our moment, m0. So that's got to equal integral from 0 to 2 of x times ax plus b dx. So that's ax squared plus bx, integral 0 to 2. Multiplying the x through, that's 1/3 ax cubed plus 1/2 bx squared, evaluated from 0 to 2. And when we evaluate, we're going to end up with 8/3 a plus 2b. Okay. Now remember that that is equal to 14/3. So if we multiply both sides by 3, just to get rid of our fractions, we'll get that 8a plus 6b needs to be equal to 14. So now what do we have? Yeah, system of equations. The thing that we love to do. 2 equations and 2 unknowns. Now there's lots of ways to solve these, and what I like to do is I like to scale one equation and combine it with the other one. So for instance, if I multiply the first equation by, let's say, 8. So 8a plus 8b equals 24. And I have 8a plus 6b equals 14. And I can subtract the two. The 8a's cancel. 8b minus 6b is 2b. 24 minus 14, oops, 2b. 24 minus 14 is 10. So what should be b? B should be 5. All right. If b is 5, what should a become? Well, so a plus 5 has to equal 3. So what is a? A should be negative 2. So the answer is our density should be, let's see, 5 minus 2x. Now, okay, is this reasonable? You should always check to see if something is reasonable. So one reasonable thing we can check is sort of say, let's think about our density at the two ends. Which end is going to be more dense, at 0 or at 2? So at 0 we're 5, and at 2 we're at 1. So that says 0 is more dense, which means that our center of mass should be closer towards 0, and it is. So that's a good check. All right. So yeah, that's it. Okay, so what do we need? We need A and B. So I guess we'll put a little box here that says A equals -2, B equals +5. Okay, cool. Whew, worked out. Now, another problem. Similar. Find the center of mass of a thin triangular plate with corners at 0, 0, 1, 1, and 1, -1. Now, they didn't draw the picture for us, but that's because we know how to draw thin triangular plates. 0, 0, 1, 1, and 1, -1. And here, it's not constant density, but our density varies. Our density varies depending on x. So that if you're, look at, say here, over at this point, our density is 1. When you get over to this edge, our density would be 1/2, because that's where x equals 1. So density varies with x. So since density varies with x, we should really think about making sure we take our slices where our density is constant. Because you always want to slice in a way that density is constant. That's actually a big theme that we have, is to say, make sure when you look in your little tiny slices, where you're looking, things are fixed. They're not changing. Okay, so what do? Well, we're after our center of mass. Now, that means we need to find two coordinates. We need to find our x bar and our y bar. That's our center of mass. I claim that one of these is easier than the other. Which one's easy? Y bar. Why is y bar easy? Why is it 0? By symmetry. Now remember, when you talk about symmetry, there's two things you need to check. The first thing is that the region is symmetric and that the density is symmetric. But in this case, we see that it's symmetric across this line, which is the x-axis. Because if you flip, your region will be the same shape if I had drawn the picture accurately. And also, your density remains the same. So use symmetry when you can. Okay, so that knocks out sort of a good chunk of the problem. But it doesn't knock out everything, which means that there's still this x bar that we have to find, which is good. Because, we don't want to have a problem be too easy. That takes all the fun out. We want to have just the right amount of fun. So mass. How do you find mass? Well, you add up from where you start to stop. It's going to be your density times your area. Now, in our case, when we think of area, we really split it into two parts. It's your height times your width. And you might say, okay, what does that mean? Well, the height, the width, is your slice. That's your dx. Your height is from one curve to the other curve. So what's our height? For a given value of x, how far apart are these two things? So this curve here would be y equals x, and this curve downstairs would be y equals -x, and the distance between would be 2x. So the area is 2x dx. Our density is 1 over 1 plus x squared. So this becomes the integral from 0 to 1, because we're going from x equals 0 out to x equals 1. 1 over 1 plus x squared times 2x dx. Now that looks like a reasonable integral to do. What does it become? Well, if you look at 1 plus x squared, the derivative of 1 plus x squared is 2x. So it looks like a du over u, which is a natural log. It's natural log of 1 plus x squared, going from 0 to 1, which becomes natural log of 2. So that's the density. That's the mass. Now that's not our center of mass. That's not our x bar. That's just how much mass there is in that plate. So for the x bar, we also need to do the moment computation. Now, do we need to have the moment with respect to the x-axis or with respect to the y-axis? Well, the reason I'm asking you the question is because we need to know. Oh, no. Yeah, you know what I was going with this. The y-axis is the correct answer. Because, remember, we said moments are with respect to a location. And so, when we're looking for the x bar, we really are looking for it when the location involved is the x location. So what we're going to do is we're going to have the same integral, but we just add a new piece, which is the x. So this last part is the mass as before. The first part is our location. And the reason we call it m sub y is x is the distance to the y-axis. Okay, so this integral looks a little bit more interesting, but just a little bit. So it's 2x squared over 1 plus x squared. And if you think back to how we did these kinds of integrals, we actually did these way back when. We would do something like this. Well, this is 2x squared plus 2 minus 2 over 1 plus x squared. And you're like, that doesn't seem like what we did, but hold on, just think. 2x squared plus 2 over 1 plus x squared, what is that? It's 2. So 2 minus 2 over 1 plus x squared. All right. This, by the way, is more tricky than we would expect you to do on the exam. Or maybe it's as tricky. It's a different kind of trick. All right, the integral of 2, we can do that. 2x. The integral of 2 over 1 plus x squared? It's 2 arctangent, yeah. 2 arctangent. Well, you had to know, if I was doing a review, at some point in the review, an arctangent had to show up. All right, going from 0 to 1. Well, we plug in 1, we're going to get 2 minus 2 times arctangent of 1. And if you plug in 0, you're going to get 0 minus 2 arctangent of 0, but arctangent of 0 is 0. Do you know what arctangent of 1 is? Pi over 4. So we get 2 minus pi over 2. If you like, you get 4 minus pi over 2. Now, where is x bar? Well, x bar is your m sub y over m. And we have m sub y, 4 minus pi over 2, over, and we have our m, that's log 2, and therefore our x bar is 4 minus pi over 2 log 2. And there we go. Now we should check a couple things. One thing you should always check is to make sure your center of mass makes sense. For instance, if we had gone a negative number, that would be a bad sign. Could we have a center of mass for our plate be over here? No. So we check. Is 4 minus pi negative? No. Okay, so that's good. Now, unfortunately, we probably don't know how to compute 4 minus pi over 2 log 2. But that sounds like it could be between 0 and 1, because it is between 0 and 1. So that's a reasonable thing. All right. Good. Now, into our final set of problems. So the parametric curve, x of t, equals t squared minus 2t minus 2, and y of t equals t cubed minus 2t squared minus 3t plus 1, crosses itself at the point 1, 1. So we're told that this point right here is 1, 1. Set up, but do not evaluate. An integral to find the area enclosed by the bulb. So in other words, this shaded thing here. So you might actually have problems that say set up an integral, but you don't have to evaluate it. So when you see a problem that says set up but do not evaluate, follow the instructions, which is to say, do not evaluate. And I know you're like tempted to say, but I love evaluating integrals and I really, really want to. Don't do it. Be smart. Don't start. So get to the setup and then be done. All right. So how do we do this? Well, to help us figure these things out, we should start by saying a couple things. Anything that we can do with curves of the form y equals f of x, we can do with parametric. And so we can find areas for curves for y equals f of x. That means we can find area for parametric. So the way we're going to start this out is we have to say, well, I need to know when am I at this point 1, 1. So to do that, we just pick our coordinate. Let's say x. That looks simpler. I know I'm going to have to be there twice. So I'm going to say, well, when does x equal 1? Because that'll tell me when I'm going to pass through that point. So that tells me I need to know when does t squared minus 2t minus 3 equal 0. Well, fingers crossed, we can factor this. Does it factor? How does it factor? T minus 3 and t plus 1. So that tells me that at time -1 and +3, my x-coordinate is 1. Now, for sanity, I should plug it into my other point. So if I plug a -1 into y, I'd get -1 here. This would be a -2. Then I'd have a +3. So that would cancel out. Then I have a +1, which is good. If I plugged in 3, I'd get 27. Subtract 18, which is 9. Subtract 9, which is 0, plus 1 is 1. So that tells me the times that I'm at that point. So I'm at the point 1, 1 at time equals -1 and 3. Now the reason that that's important is that is going to give me my bounds. Because if I'm after an integral, I need to know when to start and stop. So I'm going to start and stop at -1 and 3. Okay, that's useful to know. Now, the other thing I have to do is think about how do I find area. So I'm going to start and stop. The way I think about finding area, and the way we've done it, is we said, well, let's think about breaking things into little rectangles. So here's a little rectangle. And I say, well, how big is this rectangle? Well, there's two parts. There's a height and there's a width. So what is the height? Just think very generically. What is it? Well, the reason I'm asking the question, no. It's y, right? The height would be y. And the width, what is this? It's a small change in x, right? That's how we think about, we break things up. A height of the rectangle is like our f of x, and then dx is a small change in x. So that's how we find our formulas for area. So it sounds like it's not going to be so hard. You know I'm building up to something here. So, but okay, all right. So y would be our y of t. That's not so hard. What about dx? Now dx should represent a change in x. So you got to be careful there because you want to write in dt. But dt is measuring a change in your parameter. You can think of it as a change in time. So it's not a change in distance. So we got to convert dx into the right change in distance. So the way we do that is the dx becomes x prime of t dt. So this right here is acting as our dx. Now there's just one more caveat though. And here's the caveat you have to be aware of if you're going to do these things. So the caveat is the following. Be careful about orientation. We have been spoiled because we always think of there not even being an orientation. We've been so inundated with orientation for the last 18, 19 years of our lives that we don't even realize that there's been an orientation built into math. So we always think about, okay, I'm going from a negative to a positive. That's a direction. So when we talk about orientation for a curve, what we really want to do is we want to pay attention to how the curve moves. Because there are two things that could happen. I could have traveled the curve coming from above, looping, and then going down. Or I could have gone in the other direction. So the question is, which way did I come? From above, or did I come from below? And how could I figure it out? Well, we can plug in. Think about large negative numbers. If I'm a large negative number, what's true about y? So the large says that just pay attention to the first term. So if I'm a large negative number, I'm a very large negative y. If I'm a large positive number, I'm a large positive y, which means I'm coming in this direction. Okay, so that's the orientation of the curve. So now you see our small quandary. The dx, when I change x, what ends up happening? It's a negative value. So we fix it, and we put a negative sign. And now, we're almost done. The last thing is to say, what's y of t? Well, it is what it is. T cubed minus 2t squared minus 3t plus 1. And then there's a negative, I'll just put it as a negative 1, times x prime of t. What is x prime of t? 2t minus 2. And then we write dt. And that's it. There's an integral which will find our area. Now you might say, hold on, Steve, wait a second. What happens if we go below? Like, say here. Well, you're right. In that case, what's true about the dx? It's positive, but now notice what's true about y. It's negative. So I still have that negative. It fixes itself. It's a miraculous thing. It's like as soon as you get it to work once, it fixes all your problems. And you're probably thinking, but Steve, I can predict a problem you can't fix. Oh, I'm skeptical, my friend, but go ahead and tell me. What about this little rectangle? You just found that area. Oh, did I? Well, but notice that there's another rectangle further down. And if you look at these two rectangles, so if you look at this rectangle here, it goes all the way down, and that's positive. This little rectangle, it ends up, if you look at the sign, it's actually still negative. And so when you take the difference, you actually find the area that you do need. So it really, truly, truly does fix itself. All problems get fixed. And so it's, y times dx. And that's what it is. Now, could you do it another way? You could. You could have made your rectangles go sideways. If you did that, what would you integrate? It would be your x of t times y prime of t. Now the question is, what do we need to do with y prime? Well, let's take a look. Suppose I'm here. Well, the x is negative, and the y prime, what's true about that? It's negative. Well, that's fine. Two negatives mean I'm getting the right sign. So you don't actually need to correct. So it'll turn out that one of them will need to be corrected and one of them won't. So another perfectly valid answer is going from negative 1 to 3 of t squared minus 2t minus 2 times the derivative 3t squared minus 4t minus 3 dt. And if you work both these out, you'll see they both get the same value. So more or less, things work out really slick. Just be careful. When you have your y, it becomes y of t. When you have x, it becomes x of t. It's the dx that you have to pay attention to. Make sure you check your sign. Get your orientation. Okay, rounding the corner, almost there. Find all the lines which are tangent to the parametric curve with x of t equals t squared minus 2t plus 2 and y of t equals t cubed minus 2t squared minus 5t, and also perpendicularly intersect the line y equals 2x plus 5. Now, I have this line. If I want to perpendicularly intersect, what needs to be true? So how do I know if two lines will perpendicularly intersect? Yeah, you check the slopes. So really, this is telling us the secret code. I want the slope to be the negative reciprocal. So the negative reciprocal of 2 is negative 1/2. So this one is saying, here's what I need. I need a slope of negative 1/2. Now how do you find slopes for parametric curves? Well, y prime of t over x prime of t. Rise over run. Change in y over change in x. And we're going to set this to negative 1/2. What's y prime of t? 3t squared minus 4t minus 5. X prime of t, 2t minus 2. So now we have an equation. Cross multiply. And so we get minus 2t plus 2, because I'm going to take minus 1 times 2t minus 2, is equal to 6t squared minus 8t minus 10. Because I'm going to multiply that 2 across. Move everything to one side. 0 equals 6t squared minus 8t, and then we're going to add 2t, so that's going to be minus 6t. This minus 10, then we're going to subtract 2 more, is minus 12. Well, everything has a 6. Let's divide that out. 0 equals t squared minus t minus 2. Does that factor? Yes. It's suspicious how often things factor. How does it factor? T minus 2 and t plus 1. Which tells us that we're interested in the times 2 and negative 1. Now, is this our answer? No. Because what were we looking for? Lines. Lines. These aren't lines. These are times. Okay. So we need to change them to lines. But that's okay, because here's the cool thing. We already know the slopes. So our slope is negative a half. So what do we really need to finish our line? Points. And so the points, where do we get those? Well, we plug this into our parametric curves. So let's do 2. At t equals 2, we get 4 minus 4 plus 2, which says our x-coordinate is 2. Then we have 8 minus 8 minus 10. So negative 10. If we plug in negative 1, we'll get 1 plus 2, which is 5. And if we plug in negative 1 here, we'll get minus 1 minus 2 plus 5. So that'll be a positive 2. So now we say our lines are, let's do the t equals negative 2, y minus the y value, so y minus minus 10 makes y plus 10, equals minus a half, x minus the x value, x minus 2. And then we also have y minus our y value, 2, equals minus a half, x minus our x value, which is 5. And that's the answer. Ah, cool. All right. For the polar curve, r equals 3 plus cosine of a half theta, find the area shaded below. So we have to find this area. Now we know the basic formula for area in polar. So the basic formula for area is you integrate from an angle to another angle of 1/2 f of theta squared d theta. If you want to do the area between curves, you can generalize this and you say 1/2, you do the outer one squared minus the inner one squared. Okay, so here's the thing that we have to be careful of. When I look at these curves, it looks like it's two different curves, but it's actually the same curve, just at different times. So if you were to trace this curve out, what would happen is you start here at 0. When you get to pi, you're here. When you get to 2 pi, you're now on the inner point. And then 3 pi, you're back, and then 4 pi, you return to where you started. So you have to be a little bit careful here. And in particular, there's a temptation to say, I know what to do. It's easy. I'll just integrate 0 to 2 pi of 1/2 my function squared. Now, if you did that, would you get the right answer? No, you would not. If you integrated from 0 to 2 pi, what you'd end up getting is you'd end up getting this top part plus this part, which is not what we're after. So you have to be more careful. So you can do a couple of things, though. You can say, well, let's think about it sort of methodically. Let's first find this part. That we can do. So if I wanted to find that, what's the right procedure? Well, 0 to pi. So I'm going to go 0 to pi. And now, one thing I could actually do is, because here's the thought process. If I'm after an area, I can say I'm going to take a piece and then I'm going to subtract a smaller piece. But notice if I take this top part, subtract this little part, that's not exactly what I want. It's half of what I want. So I could now double this. So I'm going to actually double this. So I'm going to take 2 times a half, 3 plus cosine of 1/2 theta squared d theta. So that's going to give me the big thing. It actually gives me this really big thing. Now, to subtract that part, well, to do that, we can cheat and say this bluish part here is the same as the bluish part underneath. And we pointed out that if we start at pi and go to 2 pi, that's what we're going to trace out. So I'm going to subtract off 2, integral 0 to pi, 1/2, pi to 2 pi, 1/2, 3 plus cosine, 1/2 theta squared d theta. Okay, so that's what we're going to do. So the goal is, the reason we're doing 2 is this would find just sort of half the area that we want, and we're doubling it to find the total area. And we're just keeping track of sort of the outer part and the inner part. All right? With me? This is the hard part, is the setup. All right, we'll do a second one. So if you don't like this one, you'll have a chance to not like that one too. Okay. 0 to pi, and we're going to get 9 plus 6 cosine 1/2 theta plus cosine squared of 1/2 theta d theta, then minus integral pi to 2 pi. It's actually the same integral. So we really, if we can do one, we can do the other as a freebie. So the 9 is easy, the 6 is easy. How do you integrate cosine squared of 1/2 theta? What? Yeah, well, power reduction is what we call it. But yeah, it's related to double angle. So cosine squared of 1/2 theta by power reduction is 1/2 plus 1/2 times cosine of twice the angle. So cosine theta. So the 9 plus 1/2, we can actually put those two together. And so if we think of 9 as 18/2 and we put it with the 1/2, we can make this 19/2. So now we're ready to integrate. So this is 19/2 theta. The integral of 6 cosine of 1/2 theta. It'll have a sign in it. And 1/2 theta, what will be in front? 12. I wrote plus. Should it be plus? Yes. Integral of 1/2 cosine theta. 1/2 sine theta. Okay, and we're going to evaluate from 0 to pi. And now this integral is the same integral, so I can just copy it. The only thing that's different between these two integrals is the endpoints. So going from pi to 2 pi. All right, so we plug it in. So the first one, we're going to get 19 pi halves plus 12 times sine of pi halves. 12 times sine of pi halves? 12. Then we have 1/2 times sine of pi, which is 0. Plug in 0. 0, 0, 0. Okay, so that's the first one. Subtract 19/2 times 2 pi. Well, that's 19 pi. 12 times sine of pi. 0, because sine of pi is 0. 1/2 sine of 2 pi. 0. So it's 19 pi, then subtract, plug in pi. Well, if we plug in pi, we get the same thing that we had just over here. 19 pi halves plus 12. because these are the same thing. We just evaluate at pi, this subtracts evaluate at pi. Now if you stare at this, you'll see what happens to your 19 pi halves in 19 pi. They all end up canceling. But then you have 12 minus minus 12, which says 24. So you can get the answers to work out kind of nicely. So 24 is the answer, which brings us to our last one, a very similar one. Find the area of the region where x is greater than or equal to absolute value of y, and you're bounded by the polar curve r equals square root of 2 secant theta plus tangent theta. See picture below. Wow, they really wanted us to see the picture. Nice picture. Okay, so this is our curve. R equals square root of 2 secant theta plus tangent theta. Now, if we're doing a polar coordinates, this one is the kind of one we really like, because it's 1/2 integral alpha to beta of just a single curve, squared d theta. So that says what? You're really saying you're going from your coordinate, the center, to your curve. So, for us, well, we need to figure out where are these angles. Well, where are these angles? So this comes from x equals the absolute value of y. So this is like y equals x, y equals negative x. What are those angles? Pi over 4 and negative pi over 4. And now we just go from the origin out to the curve. There's not an inner part, so root 2 secant theta plus tangent theta squared d theta. So 1/2. This is a case where we can't go from 0 to pi over 4 and double because we don't have that symmetry. So we really got to work it, keep everything there. If we square, we get 2 secant squared plus 2 root 2 secant times tangent plus tangent squared. Now secant squared is great. Secant theta, tangent theta is great. Tangent squared, not so good. But what can we do with tangent squared? Rewrite it. How does tangent squared get rewritten? Well, I think it's tangent squared is secant squared minus 1. Because it's 1 plus tangent squared equals secant squared. So, this really is 1/2 negative pi fourths, 2 pi fourths, 3 secant squared theta, plus 2 root 2 secant theta, tangent theta, minus 1. Now, we're good to go. Life is good. So 1/2, 3 secant squared, integral is 3 tangent. 2 root 2 secant theta tangent theta becomes secant. The integral of secant tangent is secant. Integral of 1 is theta. So we plug these things in. Tangent of pi fourths is 1. So we get 3. Secant of pi fourths is square root of 2 times over square root of 2 makes that a 4. And then pi fourths turns out as pi fourths. Subtract. Tangent of negative pi fourths is negative 1. So then we have a negative 3. Secant of negative pi fourths, still square root of 2. So there'll be a plus 4. And then we have minus pi fourths. So that becomes plus pi fourths. Now here, it turns out that the 4's cancel. And the other terms actually add up. So what we have is a half. We have 3 minus 3, which makes 6. Minus pi fourths, which makes minus pi halves. Or if we multiply the half through, get 3 minus pi fourths. That's it. All right. Well, thanks for being here. Good luck on the test.